Have you ever stopped and asked yourself a question so simple that it almost feels silly to ask? A question so basic that everyone assumes they already know the answer. Today we are going to explore one of those questions. By the end of this video, you will discover why the Earth moves around the Sun, why gravity may not be what you think it is, and how one radical idea completely changed our understanding of the universe. Before we dive in, make sure to subscribe to the channel and click the bell icon so you never miss more fascinating and educational videos like this one. Now let's begin with a question that sounds almost too simple. Why does the Earth go around the Sun? At first glance, the answer seems obvious. Most people will confidently say it happens because of gravity. The Sun pulls the Earth, and that pull keeps our planet moving around it. That explanation feels comfortable and familiar. It is what children learn in school, what adults repeat in conversation, and what scientists have used for centuries when describing how objects move through space. But here is the surprising part. That answer, while useful, is not the complete story. In fact, if we examine the situation carefully, the idea that the Earth simply goes around the Sun because of a force starts to raise some strange and uncomfortable questions. Let's step back and look at gravity from everyday experience. Gravity is something we encounter constantly. Drop a cup and it falls to the floor. Trip while walking and gravity quickly reminds you that the ground is waiting below. It is the invisible influence that keeps your feet firmly planted instead of drifting up toward the ceiling. Because we experience it all the time, gravity feels simple and obvious. But now let's zoom out and look at something much larger, the solar system. At the center sits the Sun, an enormous glowing sphere of hot gas. Around it travels the Earth, a rocky planet moving through space in a repeating path year after year. The motion is smooth and predictable, almost like the gears of a giant cosmic clock. So the question becomes unavoidable. Why does the Earth keep moving around the Sun instead of simply flying off into space? To understand the problem, imagine a simple experiment. Suppose you tie a small piece of chalk to the end of a string. Now swing it around your head in a circle. As it spins through the air, you can feel the tension in the string pulling against your hand. Your arm pulls the string pulls the chalk, and that pull keeps the chalk moving in a circle. But there is something important happening here. The chalk does not actually want to move in a circle. According to the laws of motion, objects naturally prefer to travel in straight lines. That tendency is called inertia. If nothing interferes with an object's motion, it simply continues forward forever in the same direction. The reason the chalk stays in a circle is because the string keeps pulling it inward. The string prevents the chalk from escaping in a straight path. Now imagine you suddenly cut the string with scissors. The chalk would not freeze in midair. It would not continue circling your head either. Instead, it would shoot away instantly, flying off in a straight line that touches the circle at a single point. In physics, we call that direction a tangent. This simple experiment teaches us something important. Whenever an object moves in a circular path, something must be pulling it inward to prevent it from escaping. Now let's return to the Earth and the Sun. The Earth moves around the Sun in a nearly circular path, though technically it is a slightly stretched shape called an ellipse. But the principle is the same. If the Earth is constantly curving around the Sun instead of moving straight ahead into space, then something must be pulling it inward. That idea makes sense at first, but then a strange question appears. When you swung the chalk, you could clearly see the string connecting your hand to the chalk. That string was the mechanism carrying the force. But when we look at the Earth and the Sun, we see something very different. Between them lies about 93 million miles of empty space. No rope, no chain, no string, nothing at all. Just darkness and vacuum. So the mystery becomes deeper. How does the Sun reach across that enormous empty distance and influence the Earth? How does the Earth even know the Sun is there? For a long time, nobody had a clear answer. Then, in the 17th century, a brilliant scientist named Isaac Newton entered the story. Newton changed everything. He developed a mathematical law that could describe exactly how strong gravity is and how it behaves across distance. According to Newton's law, the strength of gravity decreases with distance in a very specific way. If the distance between two objects doubles, the gravitational pull becomes 4 times weaker. If the distance triples, the pull becomes 9 times weaker. This pattern is known as the inverse square law. With that single rule, Newton could explain an astonishing number of things: the fall of an apple, the motion of the moon around the Earth, The rise and fall of ocean tides and the movements of distant planets all followed the same mathematical principle. Suddenly, the universe seemed like a vast mechanical system operating with precise and predictable laws. But even Newton himself was uneasy about one aspect of his theory. His equations worked beautifully, but they left a troubling question unanswered. What exactly was the mechanism behind gravity? How could one object influence another across empty space without any physical connection at all? Newton called this phenomenon action at a distance, and he openly admitted that he did not understand how it worked. And that mystery would eventually lead toward a far more surprising way of understanding the universe. To understand why this question bothered Newton so much, imagine how strange the situation really is. The sun sits in the center of the solar system, and the Earth moves around it in a graceful, predictable path. Newton's equations describe this motion perfectly. With his mathematics, you can calculate the position of planets centuries into the future. Ships could navigate oceans, astronomers could predict eclipses, and scientists could understand the tides. It was a triumph of human thought. But Newton knew something unsettling. His equations explained how gravity behaves, yet they did not explain what gravity actually is. They described the result without revealing the mechanism behind it. In Newton's theory, every object with mass attracts every other object with mass. The sun pulls on the earth pulls on the moon. Even your body pulls slightly on the chair you are sitting on. The force becomes weaker as the distance increases, following that precise inverse square rule. But there was a problem. Nothing in Newton's theory explained how this attraction traveled across empty space. Think about it carefully. Between the Earth and the Sun, there are 93 million miles of vacuum. There is no physical connection, no rope, no rod, no wire carrying the influence. Yet somehow the Sun knows where the Earth is, and the Earth knows where the Sun is. To Newton, this was deeply uncomfortable. He once wrote that the idea of bodies influencing each other across empty space without any medium seemed absurd. He suspected there must be some hidden mechanism behind gravity, but he could not identify it. Let's use an exaggerated example to see why this situation is so strange. Suppose someone proposed a completely different explanation for planetary motion. Instead of gravity, imagine they claimed invisible angels were pushing the planets through space. According to this theory, these angels sit behind the Earth and gently push it toward the sun. At first, that sounds ridiculous. But now suppose this angel theory had a special rule. Imagine the angels become tired when they move farther away from the sun. The weaker sunlight makes them less energetic. If the Earth moved twice as far away from the sun, the angels would push only 1/4 as hard. If it moved 3 times farther away, they would push only 1/9 as hard. Notice something interesting. That rule is exactly the same mathematical pattern Newton discovered for gravity. If we calculate the orbit of the Earth using Newton's gravity, or using the angel theory, we would get the same result. The mathematics alone would not tell us which explanation is correct. Newton understood this philosophical difficulty. The equations worked beautifully, but they did not reveal the underlying machinery of nature. Rather than inventing imaginary mechanisms, Newton chose a different approach. He famously wrote a phrase in Latin, hypotheses non fingo. It means, I frame no hypotheses. In other words, Newton was saying, the mathematics works, the predictions are correct, and that is enough. Don't ask me to explain what gravity really is. For more than 200 years, scientists accepted this attitude. Newton's theory was so successful that few people worried about its deeper meaning. The solar system behaved exactly as his equations predicted. Everything seemed settled. Then, in the 19th century, scientists discovered something that completely changed the situation. They discovered the speed of light. Experiments revealed that light does not travel instantly. Instead, it moves at a specific speed, about 186,000 miles per second. That is incredibly fast, but it is still a finite speed. Light takes time to move from one place to another. For example, sunlight takes about 8 minutes to reach the Earth. When you look at the sun in the sky, you are not seeing the sun as it exists right now. You are seeing the sun as it was 8 minutes ago. The light had to travel across space before reaching your eyes. In everyday life, this delay does not matter. 8 minutes feels insignificant compared to the age of the universe. But for gravity, this discovery created a serious problem. Imagine something dramatic happens. Suppose a magician suddenly makes the sun vanish instantly. One moment the sun is there, the next moment it is gone. What should happen to the Earth? According to Newton's equations, the gravitational force depends directly on the mass of the sun. If the sun disappears, its mass becomes zero. That means the gravitational force should disappear immediately. In Newton's picture, the Earth would instantly stop orbiting and shoot off into space in a straight line. But here is the problem. If the sun vanished, we would still see its light for 8 minutes because that light is already on its way toward us. For 8 minutes, the sky would still show the glowing disk of the sun, so imagine the strange situation this creates. We would still see the sun shining in the sky, yet the Earth would suddenly fly out of orbit as if the sun were gone. That would mean the information about gravity traveled faster than the information carried by light. But the laws of physics say nothing can travel faster than light. This contradiction revealed a fundamental flaw in Newton's theory. Newton's gravity assumed that information about gravitational changes could move instantly across space, but the universe clearly has a speed limit. And once scientists realized this, it became clear that something deeper had to be going on. Once scientists realized this contradiction, a serious mystery appeared. If gravity could not act instantly across empty space, then the old explanation was incomplete. Something about the universe was missing from the picture. If the sun disappeared, the Earth could not possibly know about it right away. Information cannot travel faster than light. That means the Earth would continue orbiting for at least 8 minutes, even if the sun was suddenly gone. During that time, the Earth would be circling something that no longer existed. This strange conclusion forced physicists to rethink everything they believed about gravity. If there are no invisible ropes connecting the sun and the Earth, and if information cannot travel instantly across space, then what exactly tells the Earth how to move? The answer required a completely new way of thinking about the universe. At the beginning of the 20th century, Albert Einstein introduced an idea so radical that it changed the foundations of physics. Einstein suggested that gravity is not really a force at all. Instead, gravity is the result of the shape of space itself. To understand this idea, we need to step away from our everyday intuition. Our common sense tells us that space is empty and flat. It feels like a stage where events happen, but the stage itself never changes. Einstein argued that this picture is wrong. Space is not just an empty background. Space is something physical. It can bend, stretch, and curve. To imagine how this works, let's perform a thought experiment. Picture a world that exists only on the surface of a sphere, like the surface of the Earth. Now imagine that the inhabitants of this world are tiny creatures, flat bugs that live entirely on the surface. These bugs can move forward, backward, left and right along the surface, but they cannot move up or down. For them, the surface is their entire universe. They have no awareness of the third dimension outside it. Now suppose these bugs believe that their world is perfectly flat. That assumption seems reasonable from their perspective. If you stand on a large field on Earth, the ground looks flat in every direction. Without seeing the planet from space, you might easily believe it is flat. Now imagine two bug scientists standing on what we would call the equator. They position themselves several miles apart and carefully align their directions so they are facing exactly north. They check their instruments, make sure they are perfectly parallel, and begin walking forward. According to the rules of flat geometry, the kind we learn in school, parallel lines never meet. If both bugs walk straight ahead without turning, they should remain the same distance apart forever. But then something completely unexpected begins to happen. As the bugs continue walking north, they slowly begin drifting closer to each other. At first the change is tiny, almost impossible to notice. But as they keep walking, the distance between them keeps shrinking. Eventually they arrive at the North Pole and crash directly into each other. From the bugs' perspective, this is deeply confusing. They started in parallel directions. They walked straight the entire time, yet somehow their paths converged. They might conclude that some mysterious force pulled them together. Perhaps they would invent a bug attraction force that slowly draws bugs closer when they walk long distances. They might even write mathematical equations describing this imaginary force. But we know something they do not. We can see the entire sphere from outside. We know their paths curved toward each other, not because of a force, but because the surface they were walking on was curved. They were following the straightest possible paths on that curved surface. Those paths are called geodesics, meaning the most direct route available within the geometry of the surface. Their collision happened because of geometry, not because of attraction. Einstein looked at this idea and had a remarkable realization. He suggested that we might be like those bugs. We observe planets moving in curved paths and assume there must be a force pulling them. But perhaps those paths are simply the natural result of the geometry of space itself. In Einstein's view, massive objects like the sun distort the space around them. The sun bends the structure of space in its neighborhood, changing the paths that objects naturally follow. The Earth is not being pulled by a force in the traditional sense. Instead, it is moving along the straightest possible path in a region of curved space. From our perspective, that path appears as an orbit. The Earth is simply following the geometry of the universe. This idea solved the old problem of action at a distance. The sun does not need to reach across space and pull the Earth. Instead, the sun shapes the space around it, and the Earth responds to that shape. Matter tells space how to curve, and curved space tells matter how to move. It is an elegant explanation, replacing mysterious forces with geometry. But even this beautiful picture created another puzzle. If gravity is caused by the curvature of space, then we should be able to see that curvature everywhere. Yet when we look around the room, everything appears perfectly flat. So why does gravity feel so strong if the curvature of space around the Earth is so incredibly small? This question leads us to one of the most surprising realizations in modern physics. If gravity is caused by curved space, then the curvature produced by the Earth should be extremely small. The Earth is massive compared to us, but compared to the Sun, it is relatively small. Compared to the entire universe, it is almost insignificant. So if gravity were only about space bending, the effect around Earth should be tiny. In fact, according to Einstein's calculations, the curvature of space caused by the Earth is incredibly small. So small that you would need extremely precise instruments to measure it. But that creates a puzzle. When I hold a piece of chalk and release it, the chalk does not drift slowly toward the ground. It does not gently glide down over the course of hours. It accelerates immediately and hits the floor in less than a second. The effect of gravity feels strong and immediate. If space around the Earth is only slightly curved, why does the chalk fall so quickly? If you placed a marble on a table that was only slightly tilted, the marble would roll very slowly. The slope would be barely noticeable. Yet when objects fall near Earth, the motion is fast and dramatic. Einstein eventually realized that the missing piece of the puzzle was something we often forget when thinking about the universe. We were focusing only on space, but the universe is not just made of space. It is made of space-time. Space and time are not separate things. They are woven together into a single four-dimensional structure. Every object in the universe moves not only through space, but also through time. And here is the remarkable part. Even when you feel completely still, you are actually moving through space-time at an enormous speed. Right now, sitting in your chair, you might feel motionless. Your speed through space might be close to zero, but that does not mean you are not moving. You are constantly moving forward through time. In fact, every object travels through space-time at the speed of light. If you are not using that speed to move through space, then you are using all of it to move through time. Every second that passes represents a huge step forward along the time dimension. In space-time terms, you are racing into the future at the speed of light. Now imagine drawing a graph where space is shown horizontally and time is shown vertically. Every object traces a path through this graph. If an object is sitting still in space, its path goes straight upward through time. Now Einstein adds one more crucial idea. Gravity does not just bend space, it also changes the rate at which time flows. Near massive objects like the Earth, time runs slightly slower than it does farther away. This effect is extremely small. A clock sitting on the floor runs just a tiny bit slower than a clock on a shelf. The difference is so small that we cannot notice it without extremely precise atomic clocks. But the effect is real and measurable. To visualize this, imagine a vehicle driving across a field. This vehicle represents an object traveling through space-time. Most of its motion is directed through time rather than space. Now suppose the ground beneath the vehicle is uneven. One side of the vehicle is driving on firm ground where time moves faster, while the other side is driving through mud where time moves more slowly. What happens in that situation? If the wheels on one side of a vehicle move more slowly than the wheels on the other side, the vehicle begins to turn. A tank with one track moving slower will curve toward the slower side. This is exactly what happens with gravity. It is the curvature of time that pulls us down. An object moving through space-time wants to follow a straight path. But because time flows slightly slower closer to the Earth, the lower part of the object experiences a different rate of time than the upper part. This difference creates a slight imbalance in its motion through space-time. As a result, the object's path bends. To us, that bending path appears as the object accelerating toward the ground. The chalk falling to the floor is not being pulled by a mysterious force. Instead, it is following the natural path through curved space-time. And here is the surprising reason the fall happens so quickly. The difference in time caused by Earth's gravity is extremely small, but the object is moving through time at an enormous speed, the speed of light. Even a tiny distortion in time can cause a noticeable change in direction when the motion through time is so fast. Imagine driving a car at 1 mile per hour across a patch of mud. The change in direction would be barely noticeable. But if you were driving a rocket car at hundreds of thousands of miles per second, even a tiny patch of mud could cause a dramatic turn. That is why gravity feels powerful. Even though the curvature caused by Earth is small, the object is moving quickly through time, and that motion magnifies the effect. But this realization raises another fascinating question. If objects follow these curved paths through space-time, how do they know which path to follow? How does a simple piece of chalk, with no brain and no awareness, manage to move exactly along the correct trajectory? To answer that question, physicists discovered one of the deepest principles in all of science, the principle of least action. You can think of it as the principle of the lazy universe. Nature always prefers the path that requires the least effort. Whenever something moves from one place to another, the universe somehow selects the path that minimizes a certain quantity called action. In simple terms, you can imagine action as a kind of cost, effort, or expenditure. Just like people often try to take the easiest route to reach a destination, nature does something very similar. To understand this idea, imagine a situation that has nothing to do with physics at first. Picture a lifeguard sitting on a chair at the edge of a beach. The sand stretches along the shoreline, and the ocean extends outward in front of him. Now imagine that someone in the water begins struggling and needs help. The lifeguard must reach that person as quickly as possible. At first you might think the best path would be a straight line from the lifeguard to the swimmer. After all, the shortest distance between 2 points is a straight line. But there is a problem. The lifeguard can run very quickly on the sand, but once he enters the water, his movement becomes much slower. Swimming takes more effort than running. If he runs straight toward the swimmer, he will enter the water sooner and spend more time swimming slowly. On the other hand, if he runs far along the beach before entering the water, he may reduce the swimming distance, but increase the total distance he must travel. Neither extreme is ideal. The fastest path is actually a compromise. The lifeguard runs along the sand for a while, then turns toward the water at just the right point, entering the ocean at an angle that balances the two speeds. This path is not the shortest distance. Instead, it is the path that minimizes the total time needed to reach the swimmer. Now here is the remarkable part. Light behaves in exactly the same way. When a beam of light travels from air into glass or water, it bends. This bending is called refraction. If you shine a laser through a piece of glass, the beam changes direction at the boundary between the two materials. At first, this seems mysterious, but if we measure the angles carefully, we find something astonishing. The path the light chooses is precisely the same path a lifeguard would choose if he were trying to minimize travel time between two regions with different speeds. Light travels faster in air and slower in glass, so it stays in the faster medium slightly longer before entering the slower one. In other words, the beam of light automatically selects the path that takes the least time. But light does not think, it does not calculate, it does not stop and consider different routes. Nature simply behaves this way. The principle of least action tells us that the universe automatically selects the path that minimizes the cost of motion. Gravity works according to this same rule. When the Earth moves around the sun, it is not being dragged along by a rope or pushed by invisible forces. Instead, the Earth is traveling through space-time along the path that minimizes the action. You can imagine space-time as a landscape with hills and valleys created by massive objects like the sun. The Earth moves through this landscape in the easiest possible way, following the natural curve of the terrain. Physicists call this path a geodesic, which simply means the straightest possible path within a curved geometry. If space-time were completely flat, the Earth would move in a straight line forever. But because the sun curves space-time around it, the straightest path becomes a curved orbit. The Earth is essentially sliding along the geometry of space-time. When an apple falls from a tree, the same principle applies. The apple is not being pulled by a mysterious force. Instead, it is following the path through space-time that requires the least action. You can imagine the apple sliding down a gentle slope in the four-dimensional landscape of space-time. The remarkable part is that when physicists apply the mathematics of this principle, when they actually calculate the path that minimizes the action, they recover all the familiar laws of motion. The elliptical orbits of planets emerge naturally. The parabolic arc of a thrown object appears automatically. Even Newton's laws of gravity arise from this deeper principle. What once looked like a force becomes a consequence of geometry and optimization. The universe does not push objects along predetermined tracks. Instead, objects follow the easiest path available within the structure of space-time itself. And this idea brings us very close to the heart of Einstein's revolutionary view of gravity. But before we finish, we still need to step back and ask a final question. If gravity is really the result of curved space-time and the principle of least action, what does that mean for the way we understand the universe itself? So where does this leave us? We started our journey with a very simple question. We wanted to know why the Earth goes around the sun. At first, we imagined there must be some invisible mechanism pulling the Earth inward, something like a cosmic rope connecting the two objects across space. But when we searched for that rope, we found nothing. There are no chains stretching between planets. There are no hidden engines pushing them forward. The universe does not contain the kind of machinery our everyday intuition expects. Instead, we discovered something far more elegant and far more surprising. Space itself is not empty in the way we once believed. It is not just a passive stage where objects move around like actors on a platform. According to Einstein, the stage itself participates in the story. Massive objects such as the sun reshape the geometry of space-time around them. They bend the structure of the universe simply by existing. The sun does not need to reach out and pull the Earth. By curving space-time, it creates a kind of valley in the cosmic landscape. The Earth, meanwhile, does not consciously aim for the sun. It simply follows the natural path through this curved geometry. It moves along the smoothest possible route through space-time, the path that requires the least action. In this picture, gravity is not really a force in the traditional sense. It is the consequence of geometry. The physicist John Wheeler captured this idea beautifully in a single sentence. Matter tells space how to curve, and space tells matter how to move. Everything in the universe participates in this relationship. Planets, stars, galaxies, even the atoms in your body are constantly moving along the curved structure of space-time. Of course, the mathematics behind this idea is extremely complicated. Newton's law of gravity can be written as a simple equation that high school students can understand. Einstein's theory, by contrast, requires a set of complex equations involving curved geometry and tensors. The calculations are challenging even for experienced physicists, yet the underlying idea is surprisingly simple. The motion of the Earth around the sun is not caused by a mysterious pull. It is the natural result of the shape of space-time itself. For more than 200 years, Newton's description of gravity worked incredibly well. We still use it today to launch satellites and navigate spacecraft because it is accurate enough for many practical purposes. But Einstein revealed a deeper layer beneath it, showing that what we once called a force is really a property of the universe's geometry, and there may still be deeper layers waiting to be discovered. Some physicists believe space-time itself may be made of tiny quantum structures. Others imagine it as vibrating strings or networks of information. We do not yet know the final answer. But what we do know is this: the universe is far stranger and more beautiful than our first explanation suggested. So the next time you stand on the ground and feel gravity holding you in place, remember that something extraordinary is happening. You are not simply being pulled downward. You are moving through a curved space-time landscape, racing into the future at the speed of light, while the geometry of the universe gently guides your path. Gravity is not just a force, it is the shape of reality itself.